Hi, in this video, we're going to look at the process in solving problems on the lift and drag for supersonic aircrafts. Let's do a simple example first to see the main concept. The simplest object is the flat plate, with the following general conditions as shown here. The supersonic flow will cause two expansion fans and two oblique shocks. With any numerical values of the free stream conditions and the angle of attack, we can calculate the flows in region 2 at the top and region 3 at the bottom. That's all that we need to calculate lift and drag on the flat plate. We don't need to know the flows in regions 4 and 5 across the slip line. These surface pressures P2 and P3 will produce the normal forces F2 and F3, which can be calculated. The area A of the flat plate is equal to the length or chord C of the plate times the span or width W of the plate. If W is not given, we can assume W to be equal to 1 and calculate the force per unit span of the plate. Because the forces F2 and F3 are aligned, we can combine the pressures together in one bracket. Then, the lift and drag is basically the decomposed vectors of the resultant force F into the vertical and horizontal component because the horizontal component is aligned with the free stream. F is slanted at the angle alpha from the vertical line. These two equations in the box can then be used to decompose the total vector F into L and D. The final task is to calculate the lift and drag coefficients of the flat plate. The standard equations for these coefficients are shown in the box here. For supersonic flows, we need to convert ρ and V here into pressure and Mach number. That can be done easily using the Mach number equation and the ideal gas law. I recommend you to derive this equation yourself. The final equation for Cl and Cd for supersonic flows are shown in this box here. To increase the complexity a bit, let's apply this on a symmetrical wedge. The main procedures are the same, but we need to be careful in calculating the pressure forces on each individual surface in regions 2, 3, 4, and 5, and also in adding up all these forces into lift and drag. Let's see how to do this. Let's assume that we have calculated the pressures on all the four surfaces. Then, for each surface, say in region 3, we need to calculate the total force F3 acting on the surface. So, F3 equals to P3 times L3 times W. L3 is the side length of the surface along region 3 only. W is the width or the span of the wedge. We also need to do this on all the other three surfaces in regions 2, 4, and 5. The general equation for any surface I is Fi equals to Pi times Li times W, where I can be any number labeled the same way as the region being calculated. Now, let's say that we have calculated all the force vectors shown as the red arrows F2, F3, F4, and F5. But we cannot add them together yet because they are not all aligned in one common direction. So we need to decompose each force vector into its lift and drag components, which have different values for different surfaces. For example, looking at F3, the lift and drag can be easily decomposed using the equation in the box, which is the same as the ones used for the case of the flat plate. But the difference is that for the wedge, we have four different surfaces that are lined up differently relative to the free stream flow. Because of this, each surface I is inclined at a different angle theta I relative to the free stream flow. Now, figuring out this angle theta I for each surface is quite a simple geometrical problem, so we won't go into detail about that here. Once we have the lift and drag for all the surfaces, we can simply add up all of them separately, using these two summation procedures here. So we have the total lift to equal L2 plus L3 plus L4 plus L5 and the total drag to equal D2 plus D3 plus D4 plus D5. But please note that these lift and drag forces are vectors, so you need to add them vectorially. What does that mean? It means you have to take into account the signs of the vectors. For example, L3 and L5 are both positive because both vectors are pointing up. L2 and L4 are negative because both vectors are pointing down. This is because the pressure forces are pushing down on the two upper surfaces and pushing up on the two lower surfaces. The same goes with the drag forces. D2 and D3 are positive because they both push their surfaces towards the right, and D4 and D5 are negative because they both push their surfaces towards the left. With those two values L and D, we can then calculate the lift and drag coefficients using the same equations that we use in the case of the flat plate. Beyond the simple cases of the flat plate and the symmetrical wedge, we can have other cases which are still relatively simple but can be a bit more difficult in many ways. For one, it's just to add to the flavors of giving challenging exam problems to the students. In this slide, we can see a wedge that is unsymmetrical with the following parameters. The geometry of the wedge produces different angles at different corners of the wedge, and we need to be very careful in calculating the values correctly. Once we have all the angles at different corners, we can calculate the flow changes on all the surfaces. In this specific example, the angle of attack is big enough to produce an expansion fan at the top surface after the leading edge. Beyond this, we have an oblique shock at the lower front surface and two expansion fans at the middle corners at the top and bottom of the wedge. Also, notice that in this example from our main textbook, the labeling of the surfaces are different than ours. Well, it doesn't really matter how you label them as long as you are consistent with your labeling throughout the process. When solving problems, in general, we should be able to handle more complicated geometries and more realistic shapes. For example, we can have more surfaces than just the 4 surfaces of the simple wedge in our example. Imagine if we have wedges with 6 or 10 surfaces, with so many more oblique shocks and expansion fans at each corner. Or imagine that for real shapes, we may have hundreds or thousands upon thousands of different surfaces to handle. When things become more complicated, one thing that we definitely have to do is to do more calculations. Most of the times, they are just the same procedures of calculations, done again and again and again for different surfaces. In that case, it makes sense for us to write computer programs to automate all these repetitive and sometimes tedious calculations, and to handle more complex geometries. But to handle real cases, we also need to relook at the assumptions and derivations of the flow equations that we have used. For example, all the problems that we have looked so far are 2D problems with 2D flows. For 3D flows, we will definitely have flows from different sides of different surfaces, colliding and interacting with each other, with slip lines and iterative processes to handle them. All of these have to be taken into account in our formulation. But these extended cases are beyond the scope of our class. The main approach to simulate these real cases is normally to use CFD techniques. Our next video will be on solving 2 sample problems with guided steps to help you through the process.